Today we'll talk about something called von Neumann stability analysis. The background is something called Fourier analysis and Fourier transform or series, etc. I don't plan to dive into that. Instead, just maybe very, very briefly, what this does is that you have a function of, in our context, u of x and t. The x is, in this case, is our physical variable, and we're going to transform that into a function which we call u hat of c, and here the c is frequency. So you study, instead of studying a function in the physical domain, you study the corresponding function in the frequency domain. And this is a very powerful and useful tool. It has millions of applications in our particular context. It can use to solve PDE, a particular set of PDE easily, and more importantly, it gives you a better understanding of why the PDEs behave the way they do. And in practical setting, it can be used for signal processing, imaging, and fast algorithms, just to name a very few out of, again, millions of very useful stuff. Again, I'm not going to dive into the specifics of Fourier analysis or transform. Instead, I'm going to recommend 3 videos to you, 3 YouTube videos. I'm just going to write them down instead of embedding them here. This is by 3 blue, 1 brown. Alright, I think the 3 videos are called But What is the Fourier transform? And then, but what is a Fourier series? And let's say just 2 of them, 2 videos. Fantastically made, and it'll be. I hope it'll be mind blowing to you. It's highly recommended. Again, in our setting, the stuff that we do relies on one particular property. Which is, once you do this transform, you have u, and then you go to u hat. We have the L2 norm, which is you square the function and integrate. Before and after the transform, they're equal. Integrate along x or c. So this is useful because, remember, when we talk about stability, in this case absolute stability, we meant we have, again, we are talking about absolute stability. What we meant is that, well, you have time level n, un, right, which is ux at tn. Okay, you do some thing. You for forward Euler other schemes, you're going to get un plus 1, right? And what we care is how much growth is there from un plus 1 to un, right? How can we relate the normal un plus 1 to normal un? So with the Fourier analysis, we can instead we can study what about, because the U hat is the same if you talk about the L2 norm. What is this guy? What does this guy relate with UN hat? What is that? Okay, that's how the whole thing is related with this fantastic subject of Fourier analysis. Again, we're not going to talk about any details for analysis, but we're going to use it, and in particular from this particular property. Maybe another property. I just said one, but we essentially need two. Another property is that the nice thing about the Fourier transform is in the physical domain for x, if you're taking one derivative, okay, take one derivative of x, this corresponds to, for the frequency domain, c, your function for c, instead of taking derivative, you're going to multiply by I c, okay, I c times U hat. The mathematical equation in the case is that if I take the Fourier transform of Ux, this is actually equal to I c U hat. It's like multiplying by your original Fourier transform by I c. Every time you take a derivative, you multiply by I c. This, by the way, means that ut is equal to AUXX in our setting. So far we put A to be 1. Ut is equal to UXX. This would go to U hat T, right? So the transform is about X, it does nothing to T. So just steer U hat T. You multiply I c twice, you get I squared is negative 1, c squared is c squared. So it's negative A c squared U hat. This, by the way, is a very simple ODE, which you can easily solve. And the idea in PD is then you transform it back through the inverse Fourier transform, you get your U. In our setting of the finite difference method, what we have is that then they are our m plus 1's level transform is actually equals to some function, which you'll see when we do examples, of the frequency GC times the transform at nth level. All right. So then basically what we do is that we look at GC in particular. Is it increasing or not? Because if every time you advance one level, you're multiplying by GC, that means my UN plus 1 hat is equal to GC to the m plus 1's power of my U0 hat. All right. So if you want it to be stable, you don't want the UN plus 1 to blow up, then you better have a control of the GC, because you're taking this guy to a huge power, potentially infinite many steps. Of course, in reality, the number of steps is finite. In some cases, not so large. In that case, as a side remark, we actually could allow some growth. In particular, if we have this UN plus 1, if this guy is under linear growth, 1 plus alpha delta t, this is linear with respect to delta t, right? Every time the increase is proportional to delta t. If you have this, then what do we have? Then is a U capital N. What is capital N? Capital N is the number of steps towards final time. Okay, that's what we used. This again, as we did above, this is going to be 1 plus alpha delta t. Every time you get another one, have 1 plus alpha delta t. So the whole thing is 1 plus alpha delta t to the power of n times u0. Okay, u0, and we do know this delta t. So this is 1 plus alpha delta t is final time divided by the total number of steps n. All right, this to the power of n. U0, okay, 0, and the limit of this as n go to infinity, as the number of steps is infinite. So what's that limit equal to? Something we briefly mentioned in 361 as well. The essential question is, what is 1 plus 1 over n to the nth power, right? What's this limit? When n is infinite, you have 1 plus 1 over infinity, which is kind of like a 1, and 1 to a huge power, that's of course 1. But this guy is not 1, because the base is not 1, it's 1 plus tiny number. If you multiply a huge number of times of 1 plus tiny number, you don't have 1. And that's actually e, the natural number e. And this is, for those who may remember from 361, this is just e to the alpha t, right? Or from calculus, not 361. So 1 plus any a over n to the nth power, this guy actually goes to e to the a. So this is e to the alpha t times u0 norm, okay? U0 norm. So in fact, we can allow a little bit of growth without blowing up, without the final thing to blow up. All right. So remember, we need to look at the norm. All right, the norm. So this is the integration over the frequency c, which means we need to look at any single frequency. So all the possible frequencies c. All right, and want the g c to less than 1, right? To less than 1, less than or equal to 1. Again, this is only a sufficient condition. If this is less than or equal to 1, then the final step norm is less than or equal to the initial step norm. All right. Now, what do we do for that? How do we look at any single frequency? This is very important. Otherwise, later on we get lost because we're going to have a lot of notations. So by looking at any single frequency of c, that means we can think of we can treat a particular x, u of x. So for u of x is with some frequency c, that is e to the I c x. All right, e to the I c x. That's one way to do that. We can put pi there. Is not that important, but because it's a frequency, and you assume the function is equal to that particular form, right? The particular form, and of course, for us, we have the domain from 0 to 1. All right, we have this x0, x1, and so on and so forth, xn plus 1. Remember, that's a starting point of the finite difference that we did. So we are talking about we are talking about the function point values uxj, right? Uxj. Well, we know the uxj, which is u of j h, right? So h here is 1 over the number of intervals you use, n plus 1. Okay, ujh. So for this particular frequency c, the u of jh is u of I c and times x is jh. Alright, so if you just look at this final result where we have I, we have j, we have h, we have c. Alright, that's super confusing. But again, if you go back to where we are coming from, a frequency c, then it's kind of easy to understand. And also keep in mind xj is like jh. Alright, then this funny thing makes sense, I hope. Alright, now examples. So the first example is look at the forward Euler for our equation. So what we have is that we have u j n plus 1 is equal to u j n plus delta t over h squared, right? Of that u j plus 1 n minus 2 u j n plus u j minus 1 n, right? So what you do is that again you plug in what we had above. uxj is a particular form, so that is e to the I j h c, right, plus delta t over h squared. What do we have here? We have e to the I, not j but j plus 1 h c minus 2 e to the I j h c plus e to the I now j minus 1 h c. Okay. So if you simplify this thing, you'll see that we have e to the I j h c plus delta t over h squared. We can factor out one single e to the I j h c. What we have is that is e to the I h c, right? Because j plus 1 h c is e to the j h c times e to the h c, right? E to the a plus b, e to the a times e to the b, alright? So here is minus 2 plus e to the minus I h c, alright? So we can simplify this even more because we have this guy here and that guy here, right? So this is like, and also we have this guy. What is that? That's just 2 cosine h c, right? Because e to the I alpha is cosine alpha plus I sine alpha. So the sign cancel with each other, this over 2. Okay? So we ended up having, if we have this I e to the I j h c from all outside, we're going to get 1 plus h squared delta t, alright? 2, we can put 2 outside, cosine h c minus 1, right? So this guy, this is our g c. If we relate with what we did, what we just said, because, well, think about, we have this the next level is a multiple of the previous level. Okay. This, because what is this? This is just our jn, right? Jn ux u the time level n at xj. Okay. So this means the GC, the amplification factor for the forward Euler, is simply 1 plus 2 cosine h c minus 1 divided by h squared delta t. Okay, delta t. And we want GC absolute value is less than or equal to 1, again, for all c, right, for all c. And how do we do that? We know that our cosine h c, right, this is between 1 and negative 1. Okay, so this means that what we had above, the 2 times cosine h c minus 1, this is between 0 and 2 times negative 2, negative 4, right? So then negative 4. So when it's at the 0 end is fine because it's 1 plus 0, the GC is 1. So we want, which means we want when it's negative 4, we want 1 minus 4 delta t over h squared, right? This is less than 1 and then less than equal to 1 and larger than negative 1. The absolute value is less than 1, all right? Of course, it's less than 1 because delta t is positive, h is positive. So this means that, what's that? 1 minus 4 delta t over h squared is larger than or equal to negative 1. If you solve that, you're going to get delta t over h squared is less than or equal to 1/2. And which means our delta t is less than or equal to 1/2 h squared. We arrive at the same condition as we did last time. If you want to use forward Euler and the centered scheme to solve the heat equation, that's the condition you should have. You see, this is very easy. What you do is you just need to derive this, right? Derive this, come up with this factor GC, then you're all set. It's a very convenient tool. The Neumann analysis is a very convenient tool for doing the stability analysis. Let's do one more example for today. We will look at the Crank-Nicholson, and which is we have ujn plus 1 minus ujn over delta t, and we take a half of the two ends, which is 1 over 2h squared. All right, we're going to get this uj plus 1 n plus 1 minus 2 ujn plus 1 plus uj minus 1 n plus 1. And this same guy at time level n, which is uj plus 1n minus 2 ujn plus uj minus 1n. Okay? So again, you take ujn to be e to the ijh c. Again, review what we just talked about, why it is this funny thing. If you don't understand, it looks very funny and confusing, right? And you take this and then and simplify, right? And then ask, GC is equal to what for ujn plus 1 is equal to GC times ujn, right? ujn. So this is easy. We know that we have GC, right? So this is going to be we cheat a little bit. We're going to solve for this GC. So if we know ujn plus 1 is g cos c times ujn. So the left-hand side of the equation above is going to be g cos c minus 1 over delta d, alright, times ujn, which is e to the I j h cos c. And from what we did for the forward Euler, we know this guy is like e to the ih cos c minus 2 plus e to the negative ih cos c, right? This guy is the whole thing times e to the is times let's just write ujn, right? ujn. And what this guy is the same structure. So we have e to the ih cos c minus 2 plus e to the negative ih cos c. And here I'm just using what we had above. You would have to derive the whole thing. This is going to be ujm plus 1, right? ujm plus 1 at m plus 1's level. But of course this thing can be replaced by g of cos c times ujn. Okay, so what we ended up having on the right hand side is that we still have this 2 over h 1 over 2h squared. Okay, we're going to get the same factor e to the ih cos c minus 2 plus e to the negative ih cos c, right? What's left is ujn plus 1 plus ujn, which we can write as g cos c plus 1 times ujn, which again is e to the ijh cos c. Okay? Alright, so this is based on what we derived for the forward Euler, so we kind of skipped a few steps. How do we solve for g cos c? We can just simplify this equation and get rid of this guy. So we have our g cos c minus 1 is equal to, we multiply delta t on both sides, delta t over 2h squared. We have the g cos c plus 1, right, times, what do we have, the same thing, same thing as for Euler, 2 cos ch minus 2, alright, minus 2. If we call this c, right, if we call this c, because I don't want to write the whole thing, and we need to solve for g cos c, so you move everything with g cos c to the left. You're going to get, well, what is it, 1 minus delta t over 2h squared c times g cos c, right? So you have 1 on the left, and then you move things that has g cos c to the left, from the right to the left. This is equal to 1 plus delta t over 2h squared c, right? So what we have is that our g cos c is going to be equal to 1 plus delta t over h squared c over 1 minus delta t over h squared c, alright, over h squared c. That's our final, that's what we have, g cos c, right? This, of course, c is a function of cos c for a given h. So this is a function of cos c. You can plot it and you can study that. But here we can easily, for this particular, for a different function, a different example, if I give you a different scheme, you might have to plot it to visualize this and analyze this. For this particular case, it's very simple as the forward Euler. Once you are here, we need to conclude what's the condition, right? So for us, we know c is 2 cosine cos h minus 2. This is always less than equal to 0. Right? So g cos c is 1 plus delta t and h squared are both positive. So it is 1 minus something, right, C is negative, over one minus positive over one plus positive. So this is clearly, this G cos C is always less than or equal to 1. Alright, so this tells us, as we said last time, the Kronecker-Nicholson is unconditionally stable. Okay, unconditionally stable. You don't need a condition on delta t.